Hi, I'm Racing Song. I'm a master student of computer science, and this is my first semester at Memorial University. In this video, I'm going to talk about the local multidimensional scaling, as known as LMDS. It's a variant of MDS, which is a very popular method in dimensionality reduction in the unsupervised learning area. So before we go into today's topic, let's take an overview of what will be covered in this video. First of all, I'm going to show you a very simple example to introduce some background concepts like dimensionality reduction and MDS. And then we'll go into LMDS. I'll explain the algorithm so that we'll understand the core idea and know the features and to see what is it used for. After that, we'll take a look at an example from the author of LMDS. And at last, we'll see some other methods related to LMDS and recap the topic. So let's begin with a simple example. We know that IELTS band score consists of 4 parts involving listening, speaking, reading, and writing. The band score in each part can evaluate the performance of the participants in this single part. So we know that different participants, they may have different performance. Some of them have better performance in listening and speaking, like A, but not do very well in reading and writing. But some of them may have better performance in reading and writing instead of the listening and speaking. So what we want to do is to find the participants who have the similar performance in general. So what can we do that? A very common way to do this is to find the correlation between the participants over their performance. And for now, we can compare the participant A and participant B and plot each part of their band score, so we can see overall the performance of them are negative correlated. And then we do the same thing to participant A and C. We can see in the plot, they have generally the positive correlation. And at last for B and C, it's very similar to the negative correlated. So we can learn from the example that if we want to find the correlation or the similarity among the samples, we can combine their corresponding features and find some regulations. In this example, we can also plot them in 3-dimension coordinates because we only have 3 samples. But what if we have more samples or, for example, a large group of participants and we want to cluster them and find the similar samples? It will be very hard to plot them and find regulations like we already did because there will be high dimensional data, and that's why here we introduce the dimensionality reduction. Dimensionality reduction is transforming the high dimensional data to low dimensions. In this picture, we can see if we have a circle in 3-dimension space, to do the reduction, we can map it to the panels. Can choose to map it to the XOY panel, so it becomes a cycle in 2 dimensions. And to the YOZ panel, it becomes 2 line segments. The same idea can also transfer some 3D model in the 3 dimensions, and they can map to the different panels and even to the 1-dimension space. But in machine learning, we have many more high-dimensional datasets with hundreds of even thousands of features. So the specific methods to handle the reduction are very necessary. So here are some methods for dimensionality reduction. Multidimensional scaling, also called MDS, and principal component analysis, also called PCA. These are 2 of the most popular methods that can handle the dimensional reduction problem. But they're more suitable for the linear task and cannot perform well on nonlinear reduction problem. So the 4 methods listed below, the local multidimensional scaling, and local linear embeddings, isomap, kernel PCA, these are designed for nonlinear tasks. Anyway, we have other methods not listed here. So the LMDS is our main topic today, but I'll quickly introduce MDS firstly, since LMDS is a variant of MDS. So for multidimensional scaling, the main idea is to find the dissimilarity among samples by measuring the distance. Let's go back to the previous example about L-span score. Instead of using the scatter plot to find the correlation, this time we calculate the distance between each pair of samples. Here we use the Euclidean metric to calculate the distance between A and B, B and C, and A and C. So the smaller the result we get means that the two samples are more similar to each other. And the result will be visualized like this. A and C are very close, while B is far away from them. And if we have more samples, such as D, E, F, G, H, some of them may get close to each other. And apart from Euclidean metric, we also have other metric choice like Manhattan and Hamming and so on. Remember, this is not the classical MDS. In this example, we were just looking its core idea before moving to the theoretical part. Here we move to the equation. The number I and the I prime belongs to 1 to n. dii prime denotes the dissimilarities, and z1 to zn is a set of configuration points. The dissimilarities are well approximated by the configuration distances, which are the norm of zi subtracted by zi prime. And then we use the stress function as a kind of measurement to minimize the gap and to find the best set of configuration points. We can use the gradient descent to minimize the stress function. The configuration means that we can modify the distance metric like Manhattan, Euclidean, Hamming, and so on. Now we can see the idea of MDS is to find the lower dimension representation of the data and preserve the distances between pairs of points. However, since MDS preserves the distance between points, what if there are more outliers in the data? The scaling result may not satisfy, so let's move to LMDS, which is designed for a nonlinear task. The local here means part of, indicates the algorithm will use some solutions, may not take the global data. Let's take a closer look at LMDS. Well, in LMDS, it adds constraints to the pair of points. Only the points are k nearest neighbors will be considered to find the lower dimensional representation like MDS. At the same time, the points that are not k nearest neighbors will be placed in the second part of the stress function with the artificial parameter omega and d. Here the d is a large constant and the omega is the weight, which is similar to 1 divided by d, while d can go into the infinity. So what's the difference of LMDS and how can it affect the scaling? Generally, the points that are not neighbors are considered very, very far away from each other. So after the transformation, the stress function can be looked like this. The parameter tau in the second part equals to 2 times omega times d, which can adjust the distances between points that are non-neighbors. Now we can see in the stress function, the first part preserves the distances between points that are k nearest neighbors. It's the local structure. And in the second part, the non-neighbors points becomes farther away after the effect of the parameter tau. Let's look at the example from the designers of LMDS. In their article, they apply these algorithms to the sculpture data to order the sculpture images from left pose to right pose. To get the satisfying result, choosing the appropriate parameter is very important. The number of k in the k nearest neighbors and the number of tau, both of them have significant impact on the result. So in their experiments, they also applied some other dimensionality reduction methods, but none of them can outperform in these cases. as measured by the self-met criteria in Table 1. And in the table, we can also find linear method PCA and MDS are not really suitable for this task. In their article, LMDS is suitable for evaluating the similarity of image data, but it can also take a lot of efforts to find the appropriate parameters. Some other kernel methods can also deal with the nonlinear dimensionality reduction, like LLE, IsoMap, and kernel PCA. LLE seeks a lower dimensional projection of the data, which preserves the distances within local neighborhoods. It can be seen as a series of local PCA, which are globally compared to find the best nonlinear embedding. IsoMap can be viewed as an extension of multidimensional scaling, or kernel PCA. And the kernel PCA is an extension of PCA using the techniques of kernel methods. We'll not go deep into this part. We can see in the case we have showed before, these manifold methods can outperform LMDS, but it does not mean that it cannot perform well on other type of reduction tasks, since the reduction can be largely affected by the features of data and the criteria for measurement. We are almost there. Let's take a quick review. Firstly, we introduce the dimensionality reduction by a simple example. Then we explain the core idea of the distances and go into the multidimensional scaling. But MDS cannot do well in the nonlinear task, so we want to see the local multidimensional scaling, which is able to preserve the local structure as well as make the non-neighbor points farther away. After that, we take a look at the LMDS example from the designer's article. It's about ordering the sculpture's poses. And lastly, we quickly take a look at some other nonlinear reduction methods. They can be used directly in scikit-learn. This is all covered in this video. Thanks for the resources and thanks for your watching.